Thank you very much for coming here late Friday afternoon. I'm Siamak Tavallaei from Microsoft. I have my esteemed colleagues here. I'll let them introduce themselves, and we start the session.
I have this. Yeah. My name is Whitney. I'm coming from Facebook. I'm hardware engineer there in charge of AI, machine learning, hardware system design.
Hi, everyone. My name is Tiffany Jin. I'm a mechanical engineer with Facebook, also working on AI and compute systems.
I'm Richard D. I'm from Baseboard. Okay. So I'm Richard.
He won't let you speak.
Okay. I'm Richard D. I'm from Baidu, and I'm an AI system architect working on the Baidu AI computing system, and also working on the distributed training systems. Yeah.
Okay, so that was part of the entertainment, guys. You deserve it. So here we are basically to celebrate the end of the OCP Summit almost. We have one more session after this. We are almost in front of you, and maybe cocktail after this. So we'll try to go through this fast. The reason that we're getting together here is to introduce to you again detailed spec on details on the OAM, the OCP Accelerator Module. You know that artificial intelligence is growing very fast, and everybody's designing different solutions to accommodate different needs. Different accelerators are coming, and a number of different hardware platforms are forming around that. So what we noticed was that we, as industry colleagues, have been designing different platforms individually. We realize that doing individual work is hard, so we are putting together, trying to come up with the next infrastructure and next accelerator module as a common platform together. Different implementations target similar requirements anyway. That was the observation we had. We need the flexibility. We need the robustness and serviceability and reliability of individual module and chassis. Different configurations for programming, frameworks. Those are all essential elements of a solution stack. Individual modules need to be interconnected. Those are the type of things that we did not see before in other solutions. We usually need input-output outside of the chassis so that we can do scale up or scale out, depending on the solution. And we, of course, need power and cooling. So in the past, we and others have used PCIe chem form factor, but we don't believe that's the right solution. The reason for that is PCIe form factor is designed for individual cards. The solutions that we need for artificial intelligence usually fit outside of one individual module. So having multiple cards in a system is important. We need a lot of bandwidth interconnect between the two modules, and PCIe form factor doesn't do that. There has been a number of solutions around it, but it's cumbersome. We are doing that, but it is cumbersome. We would like to have a better solution. The chem form factor connector does not provide enough quality for the high-speed interconnect that we need for these individual accelerator modules. And if we do it through cabling, the cabling is rather difficult. Mavericks are there. I know some of you guys are there that are trying to make it work. And I really am proud of you, but it is very hard. So we needed a open accelerator infrastructure, and that's what we got together to produce that. We started with a open mezzanine module. For that, solving the high-density connector to increase the number of links that is possible on individual modules for interconnect. We wanted, we picked a high density connector so that the signal bit rate can go higher because the signal loss is less. We needed more space on the module itself for various accelerators themselves, for voltage regulators and power solutions. And the heatsink that we picked, the solution that we picked is suitable for air-cooled or liquid cooling. So module by itself was not sufficient. So after defining the module spec, we are putting a subgroup together. Part of you guys, hopefully all of you guys, might be part of that solution space. So we can define things around the OAM itself, the baseboard, different interconnects. One module can support multiple products. One baseboard can support multiple interconnect topologies. And a tray, a mechanical form factor to allow different kinds of baseboards, and a chassis system that can support multiple trays. And to put it all together, system management security is important as well. So those will be part of the definition that we will have. So for a baseboard, for example, we have realized that different neural networks require different topologies. You know a lot of, it's in the HPC crowd, so you know what I'm talking about. So what we thought that we do is come up with a baseboard with a grid of 8 sites for these modules. They are interconnected. PCBs are connecting wires, and wires are wires. You can run different protocols on the same wires as long as they meet the signal loss requirements. These modules can be interconnected on the same baseboard or on different baseboards in different topologies. These are some example of classic topologies. Later, Whitney is going to go through some of the topologies that are directly possible by the current definition of OAM. The modules need not be homogeneous. We can think of ways to use the same sites, the same interconnect, the same baseboard, but have different types of modules plugged in the baseboard and do different functions. Different layers of neural network might be suitable for an FPGA or an ASIC, or maybe even CPUs. You could construct a baseboard using the same wiring, but do multiple things with it. Although we're creating a spec, and spec normally is supposed to limit you, but we didn't want to limit you too much. So there's some flexibility involved. So now we can drill deeper into the OAM spec itself, because we did cover the infrastructure aspect of it as part of the server track earlier today. You can refer to that on the OCP website later. I give it to Whitney, please.
So as yesterday, we already officially contribute the spec, design specs, and also the pin mapping, detailed pin mapping, and like 3D file, and also thermal examples. So we have some thermal design as well, as we have we have the design package already contribute to OCP community, so you can go to our wiki and to download them if you're interested. This is a high level of the spec. So as you can see, we have the module here together with the heatsink design, and then the module is 112, and then 112 and 165 is a little bit bigger, but we had a lot of discussion about like how big it should be. We also consider the future ASIC design trend, and then we had a lot of discussion and collaboration with the industry, and then to define the dimension of it. And then one of the feedback we really got is some company like FPGA, right? Normally the power is kind of low, and then they may stick to 12 volt. And then we also see some of the leading companies like GPU or other ASIC accelerator, they really go far, like 300 watt we already seen, and then we are seeing the trend going to 400 watt, maybe even 500 watt. So in this case, the feedback we get, we really need to move to 48 volt. When I say 48 volt, it's actually the nominal voltage, and standard is 54. And in this case, we define this spec to support both 12 volt and then 48. I'm going to show you like how we do that. The module we defined to support total 8x16 in the module itself, and then 1 or 2 of them can be host interface, and then the rest of them, 6 or 7, can be the interconnect to each other, like on the baseboard. We already have a baseboard here. I'm going to show you the topology, how we connect to them. And in the spec, we also defined the system management and debug interface and in details. Power. The module itself, we reserved enough power pins to support up to 700 watt. In this case, we did a detailed thermal simulation. For air-cooled, we can support up to 450 watt. We can still do air-cooled. As you can see, we already have the heatsink design here. And then anything beyond 450, we expect that we need to move to liquid-cooled. So this is the high-speed connector we're using. We're using Molex mirror mass connector. It can support 50 gig NRZ or 112 PAM4. And then it has enough differential pairs for us to define total 8x16. There's a lot of differential pair there. And then this is really like high-density connector, high-density, high-speed connector. And then the interconnect, one of the things that we spent some time to discuss is the interconnect impedance. So as you can see, we have a host interface, we have the interconnect interface. Normally, differential pair, we run 85 or 100 ohm. So we pick the 90 ohm plus minus 5% as the impedance for this connector. Power. So this is the power mapping on our connector. So we have 2 connectors on the board, and then we have 2, one of them, we have the power pin. We defined both 12 volt and 48 volt. They are not connecting each other, so we can support both. One of the things, we already got that, what if over 700 watt? That's really a good question. That this is our standard, and then if we follow this standard to design our baseboard, in this case, we can put both. We can put either 12 volt module or 48 volt module, but if we want to go something different, then it's also doable, but you really need to consider like not to mix the different voltage module to your baseboard. And here is the pin mapping, how we map 8x16 to our module. So connector 0, we have 4x16, 1 for host, and then 3 for interconnect SerDes. And then we have the power defined also on connector 0, and then connector 1 basically 4x16 SerDes together with a lot of sideband pins. It's really critical when we run like 25, 28. We're moving to maybe 56 gig. It's really critical we consider, the interconnect signal integrity, that would be pretty critical. So we don't know what kind of speed we will need to support, but the connector itself will support that. And then each of the OAM supplier, they need to consider the module, the insertion loss module budget together with the baseboard. So really need to design together to see. In the spec, we defined like up to 28 gig. We hope that the OAM module itself not take over than minus 8 dB. In this case, depending on what's your die-to-die insertion loss budget, and then the rest of them will go to the baseboard. And we also defined the system management debug. I'm not going through like each of them, but we have the detailed spec listed all these functions. You can go through it. So topology. we already got a lot of questions about like topology. What kind of topology OAM can run? OAM can run a lot of topologies based on the baseboard design. So in this case, I will give an example. We did a detailed layout study, how we mapping all these, for example, 7 or 6 links together to coming out our topology. So this is an example for if you have module that have 7 links, so we hope that we can do fully connect. Means that each of the module talking to the rest of the module on the board, just one hop. This is like efficient also from latency point of view. This is preferred. Coming back, okay, yeah. So the right side, it's really the layout mapping. Each of the port, how do they map to each other, and then we consider like trace lengths to balance that design. Not working. It's not moving. I'm not connected. I think the projector died. So
we need a good accelerator module, guys.
Yes. To apply to the projector.
Give me one. Give me one.
Can I just ask a question?
Sure.
In your design study with the fully connected, what's the worst case channel module to module, including whatever assumption you made up?
You mean the trace length?
No, the
Worst
worst case channel.
case channel.
How many dBs do you expect?
So dB related to the speed. So what I can tell you is, for example, the best material, right, and then run at, I think 25 or 28 gigabit is about 1 dB per inch loss. That's the Mega 7 or equivalent PCB material. And then the longest length for the fully connect is 15 inch. So this is what I can tell from the baseboard. And then from the module side is about 2 to 3 inch total trace length. And then together with the connector, also depending on what's your speed, the connector might have some loss. Is working? Okay, cool. So you see, this is a fully connect. What if my module only has like 6 links? The same topology, same baseboard. You see the difference, same baseboard. So we take out the R to R link. Then you see the dot line, means that if your module doesn't have this kind of link, only have 6 link, and then you become a different topology. So the topology here is really what we call almost fully connect, because it basically only has 6. And same baseboard, same design. What if my link only goes to one connector? In this case, it's connector 1, and then my connector 0 doesn't have any links. That's basically based on what kind of module or ASIC you are using. And then on the same baseboard, it really becomes a topology here. So it's hard to tell, but basically the red ring and the blue ring, basically you have 2 big rings. That's the topology on the same baseboard. And for 6 links, we also have, maybe you're familiar with this since we already have some product coming out with a hybrid cube mesh. This is also one of the popular topology, which is different from almost fully connect. Okay, I'm gonna hand over to Tiffany, go through the mechanical.
Hi, everyone. Thanks, Whitney. I'm Tiffany. I'm going to go over the ME and mechanical and thermal portion of the OAM spec today. We had 2 main goals as we were designing this form factor for the OAM module. The first main goal was that we wanted to design a basic framework such that you could take different OAM modules and swap them in and out of the same baseboard. The second main goal that we had was that we wanted to have a reference design available such that any redesign could be minimal. So up here you can see the parts of the OAM itself. In purple, you can see the top stiffener. The OAM PCB is shown in green, and the bottom stiffener is shown in the light blue. In this picture, you can see a single die, but we also permit multiple dies as well in the specification.
Is there room for unpackaged memory?
Can we hold questions? We're running out of time. On the bottom view, you can see over here, there's two mirror Mezz connectors. These mirror Mezz connectors are located on the bottom side of the OAM PCB, located right here. And we also have cutouts in the bottom stiffener in order to accommodate those connectors. This next picture has the OAM as well as a reference heatsink mounted to a baseboard PCB. So that just shows the full assembly. The reference heatsink here includes a foldable top handle, 4 mounting screws, the heatsink itself, as well as a notch that we use for alignment. And we'll go over that in just a little bit. Let's take a look at the OAM PCB. The footprint of the OAM PCB is 102 by 165 millimeters. The 2 Molex mirror Mezz connectors sit at a pitch of 102 millimeters. We also have requirements on the mounting hole locations, as well as a notch size and location that we use for alignment. Everything else on the OAM PCB, in terms of keep-out zones, component placement, mounting holes for the stiffener, as well as for the heatsink, those can be up to the discretion of the OAM vendor. We don't have any specific requirements on the OAM top stiffener. However, we do have some specific requirements for the OAM's bottom stiffener. The stack height of the bottom stiffener is 5 millimeters plus or minus 0.15 millimeters. And that is just a requirement of the Molex mirror Mezz connector. That 0.15 millimeter tolerance is actually really small. So please see the specification for recommendations on how to do the stiffener adhesive Mylar stack. Also on the bottom stiffener, we have 2 3-millimeter alignment pins that sit at 5 millimeters from the center line. Those are used for alignment as well as orientation. We also have 4 die springs. They sit in 8-millimeter counterbores that are in the same locations as the mounting holes. And those die springs really assist with the unmating of the Molex mirror Mezz connector. Just because of the really high pin counts, we have fairly large unmate forces. Finally, we have 2 EMI fabric over foam gaskets that are located north and south of the connectors, and those are used for grounding to the baseboard. On the system baseboard side, we have a specific requirement of a keep-out zone of 0 millimeters. That's just to ensure that you can swap different OAM modules in and out of the same baseboard. We also have requirements on grounding pad locations. You can see the grounding pads in the crosshatched areas, as well as the mounting hole locations. And then finally, we have 2 surface mount nuts that are used to receive the 2 alignment pins that we talked about on the bottom stiffener. So for those of you who have seen the OAM module, it's quite large. And because of its hefty size and a typical very tight pitch in a system design, we do have some recommendations on how to do guidance into the system. And so we have some recommendations on stages of alignment. The first stage of alignment is actually using the notch that we described. This notch provides orientation and keying, so it prevents you from being able to flip the module and try to put it 180 degrees or incorrectly into the system. We do recommend a gap of 1 millimeter between each module in the system as well. The second stage of alignment is actually those alignment pins that we talked about on the bottom stiffener. The 3-millimeter alignment pins go into 3.6-millimeter surface mount nuts on the baseboard side. And that just means that at the end of this stage of alignment, your OAM module will be within 0.3 millimeters of its final location. Our last stage of alignment is actually the Molex mirror Mezz connector itself. The connector has a gatherability of 0.76 millimeters, and since we are already within 0.3 millimeters of our final location, we can guarantee that the OAM module will consistently and properly mate to the baseboard. Okay, so this is the OAM module plus the heatsink reference design. If you had stopped by the Facebook booth either earlier today or yesterday, you may have seen this module. We also have a system design shown with 8 of these. So if you haven't seen it, please stop by and take a look at it after this session. For Facebook, we actually have a single fruit as this module. So our OAM plus our heatsink is a single fruit, and so we never take that apart. On our reference heatsink, we have a foldable top handle. Because this module is fairly large, we specify that it can be a maximum of 2 kilograms, which is quite heavy. And so this handle definitely helps with handling. We also have 4 long M3.5 spring-loaded screws that are used to assist with easy serviceability. It's really great to have some feedback when you're sort of blindly screwing this into the system. On the thermal side, so we're going to provide the reference heatsink, all the files around that. It's a 3U air-cooled heatsink, and that will be provided as part of the specification package. We'll also provide a liquid-cooled solution as part of the package as well. Here you can see some of the information about the operation environment of the OAM. We are also going to provide some recommendations and requirements related to airflow budgeting and sensor reporting. So we are already at version 0.85 of the OAM spec. This is now available, the specification plus the entire package, on our wiki. We are also going to create a subgroup within the server project group to collect further feedback and collaborate on the OAM spec as well as the surrounding specifications for the system. We definitely invite you to join our mailing list and join our group. Here are the links for the mailing list as well as the wiki for the project. On the wiki is the specification, as I mentioned. Thank you, everyone, for attending our talk. We'll take any questions at this time.
Before the question, a comment. Everybody is noticing how large and heavy this is. But remember I talked about PCIe Chem form factor. And the size of this module, 165 millimeters by 102 millimeters. You can compare that to a PCIe Chem form factor. It need not be this big. But we didn't, as we were adding value to this particular module, we did not want to take away from you from the reference. We are comparing this one to a PCIe Chem form factor. We still wanted to have enough space for all the good stuff that they are doing. It doesn't have to be this thick if your solution doesn't need it. But as you see here, the team has designed it so that it can be as up to 700 watts. That we cannot do with PCIe form factor.
Cool. I think we're being waved at to end our session. So if you have any questions, do find us later after this session. And feel free to come by and see our hardware as well.
By the way, so we already starting to working with a different supplier to enable the OAM. By 4 and 4:30, I think Intel will have a session talking about the actual OAM module. If you're interested, you can join Intel session later. They are talking about the Spring Crest.